Hi everyone, thank you so much for joining us today for our guest speaker session. We have with us two guest speakers today. Julia Chae is a PhD student at MIT. She is advised by Professor Sara Biri. She is a Vertebrate Graduate Fellow and an NSERC PGSD Fellow. Her research interests are in robust computer vision and machine learning. We also have with us Shobhita Sundaram. Shobhita is a PhD student at MIT advised by Professor Philip Isola, and she is an NSF Graduate Research Fellow. Her research interests are in generative models and representation learning. Today, they will be presenting their recent research work, Personalized Representations from Personalized Generation. Thank you so much for taking out your time, and I'll hand it over to you.
Yeah, thank you so much, Ahmad, for inviting us. So as he mentioned, my name is Shobhita. I'm here with my co-first author, Julia, and we're going to be discussing our recent paper called Personalized Representation from Personalized Generation, which we're very excited to present at unclear this year. And so first, Julia is going to be discussing the motivation and method, and then I'll take over and talk about the results. So take it away, Julia.
Okay, let's get started.
Oh, also, do you want to mention about the questions?
Oh, yeah. So if you have any questions during our presentation, please feel free to drop them into the chat of our Google Meets link. And then one of us will work on getting them answered right away. And then at the end of our presentation, we're also going to have a live Q&A session. This work was in collaboration with Yonglong and our advisors, Sarah Beery and Philip Isola. Okay. Sorry. I'm just gonna. So we're gonna get started by contrasting the notion of general versus personalized AI systems. So in this setting, we assume that there is one AI model that many users are hoping to use on each of their unique data. And in a general AI model use case, we would normally deliver this central model to all users. And in this approach, it requires the model to be a one-size-fits-all type of solution where a single model is trained on a broad set of data and has to be able to serve all users without any further customization. And recently, we've seen some examples of extremely powerful models that are capable of meeting majority of the people's needs, such as foundation models. So on the right side, we present an alternative, personalized AI models. And in this case, each user benefits from a model that is able to be adapted to their unique data and needs. And this can sometimes actually enhance performance for the user's specific use case while maintaining privacy. So there's no need for the user to include their personal data in the larger data set used to pre-train the base model to ensure consistent performance on the data that they're interested in using the model for. And you might be thinking, like, isn't this traditional fine-tuning? So personalization can be seen as a subset of fine-tuning or specialization. But what's really unique about it is that it shouldn't require extensive input or effort from the user. And instead, these models should adapt pretty flexibly. In recent years, personalized AI models have become a pretty major focus across multiple machine learning fields. So image generation, models now can learn from just a few user-provided images or examples to generate customized concepts. One example is a work called Dream Booth, which personalizes large-scale text-to-image models to create unique renditions of specific subjects, like your dog in a country that it has never been to before. And VLM and LLM, now personalization allows models to incorporate custom concepts or unique references. And finally, in segmentation, personalization can also refine general purpose models like SAM, the segment anything model. PerSam is an example of a work that built upon SAM to adapt segmentation to user-specific concepts. So what does this actually look like in the real world? these research topics can enable some pretty important real-world use cases for personalized AI. So this is a type of model that doesn't only know general concepts, but really understands your specific world. One example is personalized search and retrieval. So instead of sifting through hundreds of images, your model can instantly find your dog in a vast photo library or retrieve the exact consumer product that you are looking for. And then beyond search, these models can also help you locate and track specific objects in the real world. So one example is personalized models can help visually impaired users find their own belongings, like spotting their shoes in a cluttered room, for example. There was a recent publication by Microsoft called Find My Things that showed that these assistive technologies can have really big real-world potential. And finally, these models in general can track what's important to you, whether it's your pet in a crowded park or your mug in a communal dishwasher. So to achieve these goals, what are the components that your model should be able to do in order for this to work? So first, let's say that we are setting up this model for your mug. So these models, first of all, should be able to adapt from just a few images of that mug. And then we want these vision models to be flexible to different tasks. So some few key vision tasks are classification, so distinguishing your mug from others, personalized retrieval, finding your mug in a collection of other objects, detection, locating it in complex scenes, and segmentation, which is precisely outlining its boundaries or masking your mug out in an image. And this isn't a trivial problem. It's actually quite challenging. And the reason is twofold. So first of all, this the problem is pretty fine-grained. So instance level problems are very challenging in general. Telling your mug apart from a different mug is significantly harder than telling mugs apart from plates, for example. And it's quite data scarce just because of the nature of personalization. We don't really want to ask the user to collect thousands or hundreds of images of their mug in order for this to happen. We want it to be few shot. So want it to be adaptive based on just a few images. Now, let's explore whether personalized visual recognition is achievable with the tools that we have available today. One obvious and straightforward approach is few-shot inference using existing vision foundation models like Dino, Dino-V2, and CLIP. And these models are models that have been trained on vast amounts of data. So they allow us to extract meaningful representations from images. And by combining these pre-trained backbones with different types of heads at inference time, we're actually able to flexibly apply these models to a wide range of downstream tasks, which is exactly what we want. But despite their capabilities, these models are actually, they struggle quite a bit with fine-grained problems. So another approach is to train new models that are specifically designed for personalization. So one option is to train a one versus all model, such as a one versus all classification or one versus all detection model. And then alternatively, we could also train a re-ID model, which doesn't only recognize a single instance, but actually is able to differentiate between all unique instances of one category, establishing kind of instance level boundaries for more precise identification. So instead of my mug versus Shobi's mug, it's able to tell that my mug is a distinct mug from Shobi's mug, distinct from Megan's mug, for example. And these approaches have really strong fine-grained performance because they're specifically designed for this task. But the one versus all model, the task must be specified at training time. So if you train a one versus all classification model, you can't apply the same model to detection without training it again. And the re-ID model actually requires large-scale instance-level data, so it can't be trained only on 3 images of your mug. It probably requires 3 images of hundreds of other mugs to really learn this meaningful embedding. So our work tackles these challenges by combining 2 key ideas: personalized generation, which I have mentioned before, and general purpose representations like clip, dino, and MAE, which are really powerful but not fine-grained enough. So by merging these concepts, we propose a personalized representation. So this approach allows us to achieve instance-level differentiation across various tasks, all from just a few user-provided images. So we're going to define the notion of personalized representation. So what we mean when we mention personalized representation is specialized representation space that encodes the knowledge about an object needed for different downstream tasks. So unlike a one versus all model, which I've mentioned before, this type of setup actually enables the model to be flexibly applied to various downstream tasks. And in our work, we show that we can learn a personalized representation from just a few real images. Now we're going to move on to method. Our setup is the following. We assume that there is an object that we're trying to target and we're trying to personalize our model to. And we have access to a small set of user-curated data set. And for our paper, we assume the size to be 3. And we have access to a general purpose vision encoder like Dino V2, Clip, MAE. And finally, the generative model that we use is a pre-trained generative model, Stable Diffusion 1.5 for our work. And the first step is to prepare a personalized generator. So here we use Dreambooth, which is a method that I mentioned before, to fine-tune a existing Stable Diffusion model to really learn our concept of interest from just a few images. And next, we use the pre-trained trained Dreambooth model to generate synthetic positives for our instance. So during this generation process, we can actually control different attributes of our synthetic data set. So one key factor is the classifier guidance score, which we denote CFG, which actually affects how closely the generated images follow the prompt. So a lower score produces more diverse but less accurate images, as shown in our slide. And then a higher score increases fidelity at the cost of diversity. We can also diversify the data set manually by varying the generation prompts. So we found in general that balancing the classifier free guidance with and using LLM prompts actually results in the best performing synthetic positive set. And finally, we're going to bring all of these steps together to fine-tune our general purpose representation. And first, we use the synthetic positives from Dreambooth that we trained and the real positives that the users provide. And then we also use a pool of synthetic negatives, images from the same instance category, but different instances generated by the pre-trained Stable Diffusion model. So these are mugs that are not our mug. And then finally, we apply a contrastive loss to LoRa fine-tune the pre-trained backbone. And this loss pushes the positives closer together and the negatives apart in the embedding space. The loss that we use is InfluenceE, and we supervise on both the CLS token and the average pooled patch features to learn both global and dense information. So moving on, we're going to discuss, once we actually have these personalized representations, how do we actually evaluate them? So recall that our goal in this problem is to show that this representation encodes knowledge about our target object that's useful across multiple different tasks. So to evaluate it, we take the trained representation and apply it to 4 different tasks to test both global and localization, global understanding and localization. So an important aspect is we want to probe directly what our representation captures. We set up evaluation tasks to use the representations directly without extra further fine-tuning, which also might require extra data. So let's see what this actually looks like for the different tasks. For global tasks, meaning classification and retrieval, we use a standard few-shot setup. We use our 3 training images that the users provide for us as a reference set, and then we encode them into our personalized representation space by computing the CLS token for these images. And then, given some test images, we encode them as well. And then we calculate the confidence score by computing the cosine similarity with respect to the reference embeddings. And once we have these scores, we can sweep over different similarities thresholds to classify these images, or use this to retrieve the top images from a retrieval set. Now, moving on to the local or dense tasks. Besides using the CLS token for global embeddings, we can also use our fine-tuned dense patch tokens directly for localization for tasks like detection and segmentation. And here we once again use a few-shot setup, so 3 training images as the reference set, and we assume access to a single test image. And we extract the reference instance patch feature by given these images, we extract our personalized patch features for each image. And then we extract the reference patch features by masking the training patch features to the object. And then we compute the cosine similarity between the mask features and the test features to get a confidence map over the test image. And finally, we binarize the confidence map with Otsu's thresholding method and upscale it to get a segmentation prediction. And we can also aggregate the confidence values over the proposed area to get a confidence score for this prediction. And one thing to note is this not by any means is a state-of-the-art segmentation pipeline, but it's a simple few-shot method to directly probe what the dense features in a representation captures without any external factors. And later, we will also show how the dense features can be plugged into more modern pipelines to improve performance. And finally, the other important component of our evaluation is the datasets. So we chose our eval datasets to intentionally cover a variety of object types, real-world scenarios, and interesting distribution shifts. The first dataset is a subset of a retrieval dataset called Diffusion 2, where the training set are images of models wearing particular shirts. And the test images are in the wild consumer images of people wearing these shirts. So there is an explicit distribution shift here between the training set and the test set. And then the second dataset that we reframe and reformulate is the dog dataset. And once again, this is using the real-world images of particular dogs. And some of the dogs in this data set are also from similar or the same breeds, which makes it really challenging to differentiate particular dogs. And for these data sets, we make sure to set aside only 3 training images to test this personalization setting. Finally, we also introduce a new data set called PODS, which stands for Personal Object Discrimination Suite. PODS contains 100 objects over 5 distinct semantic categories, as shown here. One thing to note is that the objects are highlighted in our slides for visualization purposes only. They don't actually look like this in our data set. And we designed 4 distinct test sets to capture different types of distribution shifts. An in-distribution set, pose variation, presence of distractor objects, and then finally a challenging test set with both variations. And here are some examples of generated dream booth images and negatives. So I'm going to pass the presentation off to Shobhi, who will present results. Okay.
All right. Thank you, Julia. So now let's take a look at some results. The first key question that we want to answer is quite simple. Basically, do these personalized representations actually improve performance on downstream tasks? So for the 3 datasets that Julia outlined, PODS, DF2, and DOGS, we train personalized models for each instance using state-of-the-art backbones, CLIP, Dino, and MAE, and we evaluate across the 4 downstream tasks. Now, this table compares the performance of pre-trained and personalized models averaged over instances for all combinations of data sets and tasks. And we've highlighted for each backbone, for the cases where personalized models improved over the pre-trained models, we've highlighted that with the green arrow. And for cases where performance decreased, we've highlighted that with the red arrow. And so the first main takeaway is that the majority of the time, in 32 out of 36 cases here, performance actually improves across backbones, across both local and global tasks. And also, if we average across the 3 data sets, we see, for instance, a 48% relative improvement for Dino v2 detection, an 89% relative improvement for CLIP classification. And this is just to highlight that for the compute that we invest, we actually do get substantial performance gains out of it. All this is to say that we've shown the personalized models capture useful information about the object, and also that the same representation can be flexibly applied to improve performance over a variety of different tasks. So these are 2 really important aspects. We also get some more insight into what's going on by looking at some qualitative examples. So here we've sampled some test images from PODS, specifically cases where the target object, which is once again just highlighted for visualization purposes, the target object is surrounded by distractors from the same semantic category. So for instance, we have here the target mug surrounded by other blue mugs. All right, so now we compute a similarity map between the test image and training images containing the target object using pre-trained Dino v2. And what we observe is that it doesn't discriminate between the target object and similar looking distractors. So to use the mug example again, Dino v2 highlights all 3 of these mugs as being similar to training images of the target mug. And the same goes for the other categories like tote bags and shoes. And now we show the same similarity map, but using the personalized representation. And immediately we can observe that it differentiates and highlights the target object much more clearly. Even in cases such as the tote bags or these mugs where the object is partially occluded, we actually see the occlusion boundaries have been highlighted by the personalized patch features. And another interesting thing is that if we take a look at the first mug, for instance, the key identifying feature, this carved face, is actually highlighted even more strongly by the personalized model. So this indicates that quite possibly it's attuning to the key features of the target object. Now that we've established that the basic method works in this minimal data setup, we can actually do some interesting analysis of what training data leads to the best representations. So what do I mean by that? Well, in particular, we're interested in investigating the trade-off between the compute cost of generating training data and the downstream performance of the representations. To motivate this a bit, we know that using Dream Booth works now, but it's also a potentially expensive method, right? We need to fine-tune a text-to-image model and then incur all of the inference costs. So we're interested in looking at what happens if we leverage alternative methods, potentially cheaper methods, and how those impact performance. Going back to our basic method diagram, we're basically fixing the overall method, but then ablating the generators for positives and negatives to look at different methods of generating the data. All right, so we keep the same basic setup. We have access to our 3 training images, a pre-trained encoder, and a pre-trained generative model. Now, using these fairly limited data resources, the absolute cheapest, simplest baseline alternative to using Dreambooth for positives is to literally just sample images from the limited real training set and apply traditional handcrafted augmentations like random flips and crops and so on. So this is a cheap real image baseline. And you can think of the generator as just being a function that selects random real images and then applies one of these handcrafted augmentations on top. So now going back to the performance table from before, if we take the best performing backbone from that initial set of experiments, which is Dino v2, here we've copied the relevant rows and highlighted the best performance in each column. So as we know, Dino v2 personalized with Dreambooth improves upon pre-trained Dino v2. And now we fine-tuned Dino v2 using that augmented limited training set as positives instead of Dreambooth. So this is much more computationally efficient. But as we'd expect, given that the pool of positives is much smaller, this method performs a lot worse than using Dreambooth images to personalize. And in fact, in some cases, such as this column and this column, it doesn't even improve over the pre-trained Dino v2. Okay, so clearly that didn't work well, but what other options do we have? Well, in our existing setup, options besides that real image baseline in Dreambooth are pretty limited. But as a user, we might be interested in actually expending some initial upfront effort to collect some extra labels or extra data and enable new ways of generating synthetic images. And in particular, one thing that we can do that might be interesting is to collect segmentation masks of the 3 training images. And this is useful because it provides extra information about what parts of the training images are actually relevant. Now, first of all, using these segmentation masks, we can do a simple and cheap alternative to Dreambooth called cut and paste. So here the generator is a function that independently samples foregrounds from the masked training images and backgrounds from the pre-trained stable diffusion and composes them. And then we get images such as this, where we have, for instance, these cut out mugs composed onto generated backgrounds. Now, the pro of this is that we ensure perfect fidelity by definition to the target object in these synthetic positives. So these are very clearly the same mugs as in the training data. What we lose out on, though, is pose diversity and realism. So in the case of pose diversity, we're constrained to the poses that are in the real images, right? So we lose out on, for instance, a back view of the mug or something like that a diffusion model might produce. And we also lose out on realism. We have mugs floating in midair and mugs that are unrealistically large for the background. And this is knowledge that a learned model might have provided. So positives and negatives, but overall a potential computationally cheap alternative to Dreambooth. But we can also use segmentation masks to make Dreambooth better. A shortcoming of Dreambooth is that it can learn to associate background signals from the training images with the object. And that can result in it generating images that look very similar to the training data, but can't get good fidelity to the target object without losing out on diversity. So if you remember, those classifier-free guidance images that Julia showed demonstrate that. So here, when we fine-tune stable diffusion on the training images, now we can use the segmentation masks to mask out gradients for background pixels so that the model only learns signals that are directly relevant to the object. We can also apply filtering. So now we can use DreamSim, which is a perceptual similarity metric, to compute the similarity between the masked training images, so just the object of interest, and the generated test images. And then we filter out test images with the similarity below a certain threshold. So now we hopefully get some extra diversity because the model has learned the object independently of its background. But then we also get extra fidelity because we've filtered out bad generations. And here we have some examples of what that looks like, Dreambooth with and without filtering. And if we zoom in on these 2 rows, for instance, we can see that we still get a pretty good variety of backgrounds, but now the fidelity to the target object is much better. Before, we had some cases such as these where the object wasn't even in the image or it just looked completely different. And now we get better fidelity. Okay, so now we have 2 new methods to add to this table that use segmentation masks. And first of all, we see that performance when we train on data that incorporates segmentation masks improves substantially compared to Dream Booth without masking and the real image baseline. So substantial boost here. And interestingly also, cut and paste actually performs similarly to masked Dream Booth. Now, one isn't necessarily completely better than the other. They perform better on different tasks. There isn't a consistent trend, but the takeaway here is that you can actually achieve strong performance even with a cheap alternative. And the natural next question is, given that they seem to perform differently in different scenarios, what happens if you actually train on a combined pool of cut and paste and Dream Booth images? So that was what we did next. And it turns out that that's actually what gives the best performance. So the important takeaway here is that incorporating learned models like diffusion models does seem to provide important knowledge for getting the best possible performance. But if you're a cost-conscious user, for whom getting the best possible performance isn't the highest priority, then you can still get strong performance with a cheap alternative that doesn't make use of fine-tuning text-to-image models. So this is getting back at what I said about a compute versus performance trade-off. Now, besides segmentation masks, another natural source of extra data is the internet, right? Let's say we don't want to use a text-to-image model to generate backgrounds for cut and paste or for negatives. Well, there are lots of publicly available data sets like ImageNet and Coco and so on that have thousands and thousands of photos of mugs and screwdrivers and generic backgrounds that can be used for this purpose. So that was the next experiment that we ran, was to replace images that were generated with the pre-trained stable diffusion with internet-generated images and see what happened. And in particular, we took this best performing combined data set, and as I said, we replaced the cut and paste backgrounds and the generated negatives with internet images. And that's what happened. That's the final row of this table. And interestingly, it doesn't impact performance in a consistent way. So we didn't find a consistent trend or difference between using synthetic and real images there. Okay, so to summarize the main takeaways from this section, first of all, we've found pretty concretely that incorporating synthetic data, that's these rows, performs much better than training on the limited set of real images only. Second of all, that both Dream Booth and cut and paste lead to good representations. So for a user that's conscious of cost, an option that yields strong results is to use this sort of cheap alternative where you invest extra time into getting segmentation masks. But finally, that sampling from the combined pool is best. So this means that there is information in learned models that gives valuable extra information for getting the best possible performance. And to summarize, we found this interesting performance versus runtime trade-off. All right, now as a user, a final, more expensive, but something that you can do upfront action that you can do is to actually go out with your camera and collect new images of your object. So our final ablation is to see what happens as we scale up the size of our training set. And to do this for a subset of the pods data set, we actually went and collected extra training images. And then we fine-tuned DynaV2 using those expanded real data sets, and then on those expanded real data sets plus the best synthetic data method. And that resulted in this plot. So on the x-axis, we show the number of real images increasing, and on the y-axis, the classification accuracy of representations learned from the expanded real image sets, and then the expanded real image sets plus synthetic data. And the key thing to note here is that in every case, synthetic data helps. It scales quite well compared to real data. And even after real data saturates, meaning you've reached the point where extra real data isn't helping, you actually still get a performance boost from adding synthetic data. And this is really important because it reflects, this plot reflects scaling with the current state of generative models, but this is also going to improve as generative models get better. So this is quite an optimistic outlook on the potential scaling of this method. Now, another important analysis question is how well these personalized representations generalize to in the wild scenarios and distribution shifts that aren't reflected in the limited training data. So, if you were to train a personalized model on your object and then you put that object in a far-flung location, would your model still work? Well, we can start out by looking at some fun qualitative examples. So here we have sample test images in the leftmost column, and then on the right we have examples of positives, meaning images that show the same dog that have the lowest DynoV2 similarity to the query. So these are intentionally hard positives. And as you can see, there are a ton of different distribution shifts here. We have the dogs in completely new poses, different lightings. In this case, the dog is almost blending into the background. We have different zooms and camera angles and locations. And if personalized DynoV2 was robust to all these shifts, we would expect it to compute a higher cosine similarity with the test image. And that is indeed the case. So these are some examples of challenging cases that are adversarial to DynoV2, where we see a substantial improvement with personalization. Then here we have some hard negatives instead, meaning we have images of different dogs that had the highest DynoV2 similarity to the query image. So here now we would hope that personalized DynoV2 has a lower similarity score than pre-trained Dyno. And for the top row, that is indeed what happens. So this shows these are pretty challenging even to the human eye. These dogs look pretty similar to the target dog, but DynoV2 personalized is able to differentiate it a bit better. But for the bottom row, the opposite happens. DynoV2's similarity actually goes up. So this is an example of a failure case where it's confusing different dogs that look very similar with each other. So these qualitative examples were interesting, but next question is, can we actually quantify what types of distribution shifts the models are robust to? And it turns out we actually can, because if you remember, we had incorporated these different test splits into the pods data set to test pose variation, distractor variation, and then robustness to challenging settings that have both. So this plot shows the performance of DynoV2 personalized with the different data sets that we had studied broken down by these different pods test splits. So x-axis is the test split, y-axis is the classification performance. And the first takeaway is that all of the representations with synthetic data outperform the real image models. And this makes sense. They saw much more diversity of data. And interestingly, that the margin, the gap between them, increases the harder the splits get. Second, and most interestingly, we see that there are differences between the performance of models trained on different synthetic data. So for instance, Dreambooth trained models perform better than cut and paste trained models on pose variation. And cut and paste performs better for distractor objects. And we can look at some examples of what this looks like. All right, so here we have examples of images and then the cut and paste and Dreambooth predictions, model predictions of whether they're the same or different. And we see that for positives that are in different poses, or in this case, negatives in the same pose, cut and paste trained representations fail more often than Dreambooth trained representations. And on the other hand, for negatives that are very visually similar, shown over here, Dreambooth trained models tend to confuse them more often than cut and paste trained models. And what's really interesting is that we can actually trace those strengths and limitations in the models back to biases in the data sets that were used to train them. So if you remember, we discussed in cut and paste, there's this lack, cut and paste data sets, there's this lack of pose diversity. So the model, despite seeing different backgrounds, will only see the poses that were in the training data set. And this might explain why cut and paste models are less robust to pose variation. On the other hand, mass Dreambooth images have a great variety of realistic pose variations, but often fail to preserve the fine-grained details, which maybe can make the models less robust to fine-grained shifts. All right, so now in the final section, we're going to take a look at possible applications or extensions of personalized representations. And in particular, as Julia mentioned, our few-shot evaluation strategy was great for probing the quality of the feature, but in practice, we want to be able to plug these models into state-of-the-art pipelines. So for example, for segmentation, no one's really using Otsu's thresholding method to get a segmentation mask, right? They're using SAM. So we actually took a look at this paper called PerSam, which is a method for adapting SAM to personalized segmentation using a reference image. So for instance, we have this dog, and then we can use PerSam to get personalized segmentations of it. This is the method. It's kind of complicated, but the relevant part is over here, where the method uses DynoV2 to extract patch features of the test and reference images, and then use that to guide to the SAM segmentation. And we basically asked, what if we take DynoV2 and we just drop and replace it with DynoV2 personalized to this dog? Will it actually improve PerSam's segmentations? And it turns out that it does. So here we show, for all three of our data sets, we compare the performance of PerSam when using pre-trained and personalized DynoV2. And in all cases, we see a pretty substantial performance boost. So this is exciting because it shows that outside of our few-shot evaluation setup, these models can potentially be basically plugged in to existing state-of-the-art pipelines using big models like SAM and still allow you to see boosts in personalization performance. Okay, so now just to wrap up and summarize what we've gone over. In this project, we used personalized generative models to adapt general purpose representations like clip and dyno to be personalized representations using just a few images. These representations consistently outperform general models across multiple downstream tasks, which is important because we want that flexibility. And finally, we can leverage extra upfront resources to get some computationally cheaper alternatives, and we were able to explore this cost versus performance trade-off. And finally, we introduced the PODS dataset, which we really hope is going to be a valuable benchmark for a variety of different personalized vision tasks, including the one that we've laid out in this project. And just to remark a little bit on the outlook going forward, we really want to emphasize that our model is not limited to existing generation techniques. Generative models are going to keep getting faster, cheaper, more accurate, more controllable. They've already progressed so much just since we started this project. And so we see that as a really positive thing for this whole line of research. And we hope that this work is just going to, that these results are just going to keep improving as generative models improve. And that wraps up our presentation. All of our code and all of our synthetic and the PODS data set is available on our website, and we'd be happy to take any questions. Oh yeah, did somebody raise their hand?
I think so.
I have a question. So, great talk, by the way. So, have you tried it with multi-object personalization? Like, for example, if I want to personalize on my multiple objects, do I need to train multiple models, or should I just include multiple images of multiple objects to train a same model?
Yeah, that's a great question. I think we did a preliminary exploration of that, but it wasn't really. I think the focus of this paper was more of the proof of concept of personalizing to a single object, but we definitely, I think, a possible future is a model that's personalized to your desk, for instance, where it's personalized to all of the items in your desk or your home. So I think it's definitely something that would be great to explore, but maybe it would take a little bit of tuning.
All right, and I have one more question. So generally, from what I have tried with Dream Booth, it works well if we provide it 15 to 20 images, especially like most of my use case was fine tuning on human images. But I'm not sure if it works well with 3 to 5 images on of the objects that are not human. So maybe that's something you have considered.
Yeah, so it's definitely true. Dream Booth has limitations with small numbers of images, and that was definitely something that we ran into, as you could probably see with our with the example generations. So I'll say two things. One is that, as you saw, incorporating segmentation masks and disentangling training when you disentangle the foreground and background helps substantially to improve them. But also, oh my God, I just lost my train of thought. The second thing is that, oh my God, I forgot what I was going to say.
It's all good.
Do you want to?
Yeah.
Oh,
Sorry. Yeah, I think in general, you make a really good point, and we did present an ablation at the end of our analysis section that did collect more real images. And in that ablation, when we collected more real images, we actually retrained the DreamBoost model with those additional images, so that increased the quality of our synthetic set. And we have consistently observed that when we collect more images and it increases the quality of our synthetic set, it's because the synthetic set is of higher quality, it's able to still provide additional information over the real data set that we have collected, making our personalized representations more robust to the ones that have only been trained on real data.
I just remembered the other thing I was going to say, which was that because we're using a contrastive loss, it often doesn't, like, the images don't need to be perfect. And I think, for human faces, we're super attuned to like very fine-grained variations. But in this case, you actually only really need the positive to be more similar to the training positive than to the negative. So the loss is pretty robust against failures in the generative model.
Makes sense. Thanks. And one last question that I have is that when we are personalizing with clip, is there any way, like, have you tried to
I
use
did.
the text encoder?
Sorry, could you repeat the question? I think it broke up.
So using clip text encoder to personalize. So in that case, we can, especially for search or search cases where we can, modify it with the text prompt.
Yeah, I think that would be a really cool extension. In this case, we only focused on the image encoders, but there is another work called Palavra that I think personalizes the text encoder as well in some way. So yeah, and there's also some VLM works that explore that as well. Some interesting concurrent works.
Thanks.
Yeah, to comment on that, so like Siglip 2 just came out, so you can like extend this work or like compare with like the differences between Clip and Siglip and how they kind of perform in the various downstream tasks.
Yeah, for sure. And Siglip 2 I think has just quite very strong performance on fine-grained tasks especially. So I think that would be interesting to look at how that compares.
Yeah, I had a query. What's the since you used Dino V2P, so is P specifically personalized fine-tuned model that you used?
No, so here's the case for me. So Dino V2P just denotes the personalized with our method. So this is comparing so if we personalize to each instance and then we average the performance over the instances, and then we compare that to doing the same thing with pre-trained Dino. So does that answer your question? I hope.
Yeah. So that's
the P just indicates that this is Dino V2 with our method.
Okay, cool. Plus, like, I had a query regarding like in the latent space. So, have you like other than the info NCE loss that it's like very much common nowadays. So, do you guys have any plans to like play around in that space? Since I think if you try to improve the performance, if you attack that plane, I think so you will get the since like you have these kind of images that has to be the how do I put it like in the info NCE laws you have those reference and the test set of images that have to be pushed and pulled apart. So like I was thinking, yeah, how do you see that evolving?
Yeah, sorry. That's a really good question. We definitely considered other losses while engineering our method together. So we tried multiple different versions of contrastive losses, not just influency, multi-positive, hinge losses, triplet losses, and we also tried supervised losses that doesn't require any negative set, which in some ways might be more, such as cross entropy, and that might be more computationally efficient at generation time because you don't have to generate these pool of negatives. We ended up finding that influency has significantly superior performance over the other losses, but I think it's pretty loss agnostic. We're happy to explore other methods in the future if they end up being able to provide a really powerful like metric loss signal to be able to enable this type of personalization. But that's a really good comment.
Yeah, cool. Thanks.
All right. Thank you so much. I guess seems like a good place to wrap up then.
Yeah, thank you so much for your time.
Yeah, and thanks so much to everyone who came. And yeah, please feel free to reach out.